This talk has the slightly snarky subtitle, 89 Easy Steps, and I've had some people actually ask me how many real steps there are. There's not a particular number of steps. The point is that writing libraries is hard, and there's a lot to cover. These talks are 1 hour, so I jammed kind of a lot of stuff into this 1 hour. So if you have a question that you think really clarifies something, feel free to jump in anytime, but if you can, kind of minimize your questions, because there's a lot to go through, especially in the second half of this. Okay, so things I'm going to cover. First of all, why we write libraries at all. What's the point? Efficiency concerns, usability concerns, and then last I've got sort of a grab bag of useful implementation tips for writing libraries. So first, motivation. What is the principle that governs what we need to think about when we're writing a library? The reason we write libraries is, of course, code reuse, right? So there is no other reason. Right, you've got code that you write every day. Some of it is meant to be reused, and hopefully that's library code. And some of it is one-time use or very custom, and it's not suitable for reuse, and that's your application code. So this is going to underpin everything that I tell you in this talk. Right, we're trying to achieve this good reuse. Okay, so what is the main difference between the two? We've got library code and application code, and we don't know the requirements for our library code when we write it. We don't know what the user is going to be needing this library for because we haven't met them yet, okay? And sometimes you don't have very good grasp on what you need for your application requirements either, but to the extent that you know them less for a library, usually a lot less. So as an example, let's say I've got my application, I've got this button type, and for the button, I have a click handler. Okay, so whenever you click the button, I get this function as a callback. And how much time do I have to do something in this function? Does anybody have a guess? You can just shout it out.
Yes, 100 milliseconds.
100 milliseconds, good answer. 100 milliseconds is what I said too, because usually, like, if you have around 100 millisecond response time for that, no one's going to notice, right? The user cannot detect that lag in feedback. What if I have an arbitrary function called foo in my library? How much time do I have there? I don't know, right? And nobody knows. So the point is that I don't know if someone who calls this is going to call it inside of a hot loop, or they have, like, a few nanoseconds is the overhead that they're allowed. I don't know if they've got 100 milliseconds or somewhere in between or something else. No idea. So we need to make our library as usable as possible for anyone that might want to use it. And the and no more part is important. Okay, it's easy to get carried away with this. I'll get into that in a little bit. But this implies that we need to care about efficiency because this is C++, people care about efficiency, but moreover, we need to make it maximally efficient because we don't know the use case. We don't know when that person is going to be calling that function, how it's going to be used, what the time budget is. And for the same reason, we need it to be maximally reusable. We need it to be composable with other things we're doing and reusable just in a functional sense. Okay. Anytime you write code, there's two audiences you have to care about. There's the compiler, so the compiler can reason about and compile your code and it's correct. And you also care about the reader of that code. So when you're writing an application, especially if it's like demoware, some kind of throwaway thing, you just write it once and then you throw it away. You don't care about the user being able to reason about the code. When you write library code, you really care a lot about that end user, right? And it might be you in 6 months or someone on your team, or it might be a complete stranger. Okay, so as far as the motivation goes, what have we covered here? We care about libraries for code reuse, and these are two corollaries. We care about maximum efficiency and maximum usability because of the primary principle 0, okay? So, efficiency. Everybody in this room is a C++ programmer or something like that, and we all know lots of guidelines for making C++ efficient, right? So you make your moves no except, you minimize copies, you minimize resource allocations. There's lots of things like this. But these are all implementation guidelines, and what we need to do is lift those implementation guidelines into guidelines for how to make interfaces. I wish I had some really concrete silver bullet type guidelines for this part, but I don't. So we're going to look at an example. Since we don't know the usage context, this is going to be a very ad hoc process, right? It's going to depend on the specifics of your library and its interfaces. Okay, so a way to get a sequence of things out of an API. This is a bad implementation, or bad interface rather. I've got a struct x, I've got a function numx's that tells me how many I have available from that interface. And then I have a function that gets one x at a time by the index, okay? And if you give me an out of bounds index, I'm gonna give you a null for that pointer to x. So this is how I use it. I just get the number of x's on the stack, I loop over them. Because I've chosen to write this into this loop where I'm consuming only the number of x's that I know I already have, then I don't have to check that it's null when I get it back, and I just use each one as I get it. Okay, so the implications of this are that inside the library code, you have to check that the I that you're given to get x is in bounds, right? You might have to check on both sides or just one side of the range, depending on how you write it, but you're gonna have order n branches that are not strictly necessary. In the receiving code, in the client code, you have to check that the x you get back is not null if you don't use it in something like that loop. In the general case, if you're given an index I, you don't know if it's gonna return a null or not at one place in the code, or it's very hard to reason about that, so you have to do checks there too. You've also got order n function calls, which is a lot more than I would like. So we want to take this same thing and we want to minimize the number of branches and minimize the number of function calls. So a C way of doing this would be that you get the number of x's and then you give it an array that has that many, a room for that many pointers in it, and then it fills in the array with pointers to all the x's that it has. Here's how you use it. You just take the number of x's and then, because of C++, you probably put that in a vector and you resize the vector to be that size. Then you call getX's one time and then you loop over all the x's and use each one. So this is better because we only need to call two API functions, right? So that's a lot less than the order n function we claimed before. And there's no more per element branches inside the implementation. So that's definitely an improvement. But we still need to allocate memory to use this. And if we just wanted to look at the elements, that's really not appropriate. Right? We don't force someone to do memory allocations just to get a look at what's in the what's behind the API. Okay. And in this case, we happen to have a function that tells us the number of x's. But what if the way we're getting these x's is that they're coming over a wire, they're coming from a terminal? We don't know the exact number of them. So again, it's limited by that. So a better way to do this would be to construct a lazy range. Okay, I've called this one X range, and as you can see, it's just got a type def for the iterator of the underlying storage that it delimits a range of, and then it's got a first and last member, and that's it. I just define a public member, public function, free function rather, begin and end for getting the first and last members, and then getX just returns one of these X ranges. And then here's how I use it. I just say, give me the range, and I'm going to loop over the range in a range-based for loop. Right? Very simple. If I decide that I do want to copy the elements out, I can still do that too, just by copying the sequence, like you see down here at the bottom. Okay, so that's a very straightforward way to do it, and it has the nice property that it handles unbounded sequences as long as you change that iterator category, right? Where that was a random access iterator, but if I change those to input iterators, then I could have something coming in from a file, or something coming in, a stream, or something coming in from a wire. Okay, so you need your API to be efficient under all reasonably foreseeable usage scenarios. And I mean reasonable, okay? Don't go crazy. This is something you're gonna hear me say over and over again. You want your interfaces to be maximally reusable and maximally efficient, as I keep saying, but there is an easy way to go off the rails with this stuff. So you have to use some judicious amount of inclusion and exclusion of what goes in your APIs. So to get to that point, as far as efficiency goes, keep saying, like, what if I called the API like this? What if I called it like that? Okay, and there's going to be some point at which you say, well, what if someone could do it this way, but think about, like, in terms of use cases, like, realistically, is someone going to want to use it that way? And if not, then that's not a real use case, and don't worry about it. Don't say that, like, I need the data to be accessible in every possible permutation of access, because it's just not realistic. Come up with concrete use cases for what works, and then make sure every one of those is maximally efficient. Okay, so that, in other words, don't get crazy with that. Okay, so usability. I'm not going to dwell too much on efficiency because I feel like as a community we have a really good handle on efficiency, and I feel like we don't have a very good handle on usability. So that's where most of the talk is going to be spent now. So this is hopefully a non-controversial thing to say, that names are important, but I want people to think that, what you usually hear is don't use unintuitive names, but I want to take it a step further and say I want your names to be obvious. So getting things from a sequence, or selecting things from a sequence you've already gotten. In this case, I've got a struct x with a value member. If I've got a bunch of x's on the stack, and I've got another vector of x's that I'm going to select from the other range of x's, I call this filter function. Okay, filter is not doing anything crazy. It does kind of what you expect. You take a begin and end iterator and it just stuffs stuff into the selected x's via the back inserter, and it has a predicate to tell you when you do something. But my question for you is, what is the something? Does it filter in or does it filter out? If you come from the functional world, you expect this to, you're looking at me, I see, because you expect it to filter in. And everybody that comes from the functional world expects it to filter in. The problem is that I've worked at a place where we had multiple filter functions, some of which filtered in, some of which filtered out. You just had to know which one was which. And if someone doesn't come from the functional world, they might think, well, a filter like filters out grit out of your water line, so this is probably filtering out, right? So the impedance mismatch you get from people with different backgrounds means that this is not an obvious enough name, in my opinion. Instead, what if I called it copyIf, which is what the standard algorithm is called that does this? Now it copies if the predicate is true. There's no way for me to misunderstand this, right? Besides being tragically behind on my sleep, right? I mean, like, unless you have a complete brain fart, you're going to understand what this does. Everyone here is comfortable with this name. Okay, so again, don't just try to go for intuitive names, whatever that means. I want the names to be obvious. I want it to be like, there's no way I can misunderstand what this thing does. The name describes what it does completely. And when I make a guess as to what I think the implementation is, my guess is going to be right because the name was well chosen. Okay, the principle of least surprise is another one that's probably familiar to people. So don't make your interfaces do crazy things that no one's going to guess. So for example, if I've got this register function, right, it takes a pointer to x. If I knew an x on the stack and then I call register x, I feel like I'm using the API right. Maybe it doesn't have API docs, maybe I just see the name of this function and I see that I need to register stuff and I would proceed to use x after this. But then when I get a crash, I look at the implementation of register and I realize that this is actually, should have been called consume or something, but someone named it register instead, right? How was I supposed to know that? Like, I'm not psychic, right? And the name is very misleading. Names are important, and really, I think that in many cases, the principle of least surprise is just a permutation of names are important. So make your interfaces impossible to use incorrectly whenever that's possible. And if you can't make them impossible to use correctly, make them very difficult to use incorrectly. Impossible to use incorrectly, I should have said. Okay. So what happens when we try to restrict the number of x's in that example before, like the bad interface for getting x's, right? We get the number of x's, we have some code that mutates that number, and then we loop over the x's that we want to look at. Well, if I write that code that mutates the num variable such that num exceeds the number of x's, then I get undefined behavior. Hopefully I get a crash, but maybe I just get an undetected bug for months that I have to deal with down the road, okay? So if we use that range-based approach I was talking about before, not only is it, I'm arguing, more efficient, but also is disallowing direct indexing into that range in most cases. So the example I showed you, those were public data members. If you make them private data members, then you don't have people indexing into that, okay? Alternatively, if those were input iterators, it wouldn't matter that they were public because, again, you can't index with an input iterator either. So you give up some, you give them some flexibility because you can't do something like, give me from the third to the eighth element of this range, right? That flexibility is gone if you can't index into it. But many of the sequence operations that you're going to do are going to operate on the whole sequence. That's just the nature of many use cases for sequences. If that is the case, make it impossible to index into the sequence because you obviate a whole class of errors that you could otherwise be vulnerable to. I already said that. Okay, another one is avoid aliasing. So that means don't use pointers and references in your APIs because that allows you to alias values in those interfaces. So that confuses you when you're implementing, that confuses your users who are using the API, and it confuses the compiler too. The compiler generates worse code when you do that. So here's an example. It's a pretty classic example of a wrong implementation of XOR swap. Does anyone know why this is wrong? Anyone? If A and B are the same, the first statement zeroes them out, okay, or it out. It's the same thing. So if I pass in A and B, but they're the same object, instead of swapping with itself and becoming a no-op, it actually zeroes that thing out. So as I told someone before, if you really don't care about precision, 0 is pretty close to everything in the max int range, right? So if that's the only condition under which this is correct. So this is a possible implementation of a fix, right? So if I know that these are different objects, then I can just only do the operations when I know that they're different objects. So This is bad because we've got an extra branch in which would be a very simple, straight line, highly efficient little bit of code. And I don't want to have to think about identity. This is almost more important to me, right? I don't care that these guys point to the same place in memory. I care that they're the same value. That's the thing I want to reason about in the code. Having to reason about lifetime and who's who is taking you away from what the program actually does. It's making you think about stuff that you don't need to think about and complicating your life. So how about this implementation? Now we copy out the references we're given onto the stack, we do our operations, and then we copy them back out, okay? So this is better, it's correct, but this is also good too. And if I just copy them in by value and then copy them out by value, it's a pure function. It's still simple straight line code, and it turns out, believe it or not, I used Clang 3 something to generate code for all these, and this actually generates the tightest code. Don't use stood pair for this if you want to generate tight code. That's not going to happen. The stood pair version of it generated almost twice as much code as any other implementation. So, the bottom line here is that you should avoid references and pointers in your interfaces because they make it harder for you to write a correct implementation, and it makes it harder for your users to understand the right way to use your interface. Sometimes references are unavoidable. I'm not saying anybody should pass in a large object by value and not pass in it by const ref. That's not on the table. But if you're doing small values like I just showed you, the convenience of writing swap where it does references might actually be a pessimization. And you need to look at the code that your compiler generates to determine if the references are a win or a loss. Like when I first did this, I did it in terms of stood pair, and I thought, okay, well that's easy, right? And then I looked at the code that it generated, and I was like, this is terrible. So you got to look. Okay, another example, if you have a base class and a struct s derived from base, let's say you have some index, some notion of index for a base, and not every base has an index. So the API author decided that they were going to return this index unsigned int as a pointer because it's nullable. You can say like, well, if there's no such index, then I'm going to return null. And then there's a convenience function, new s with index, that dynamically allocates an s, calls getIndex, and returns both of those things to you, okay? If I'm going to use new s with index, and this is all I know, I just see this stuff, then I immediately have some questions about what it's doing and when it's safe to use and how best to use it. So if I just think of the simplest implementation, this is what comes to mind, right? I just new an s, and then I call getIndex with that new s, okay? Does getIndex throw? I mean, it returns a pointer, and so it's going to return a null in cases where there's no such index. But in the general case, I can't just say like, well, I can depend on the fact that doesn't throw. It's C++, just any line of code you have to suspect it might throw at some point, okay? So given that, if the answer to that is yes, then does that mean that the whole thing throws? Does num s with index throw? Okay, if it does, it's going to leak that s, right? There's no cleanup for that s, it just gets leaked. So if it doesn't do that, if it swallows or captures some exceptions, is it swallowing the exceptions? Does it pass them through? I need to know these kinds of things, right? So here's an alternate implementation. I didn't change the pointer from getIndex, but I did change the new s with index to return an s by value. It could also return one by Unicode, right? Those are kind of equivalent as far as I'm concerned in this case, because what I get is something that I no longer have to think about and understand how it works. I know the semantics of it by looking at the interface. So the question of the first one is, I don't care, because if getIndex throws, everything gets cleaned up, and then whatever getIndex throws, new s with index can pass through the same thing. Like someone could have made it swallow exceptions or do something crazy, but it's unreasonable to expect that, right? The way I'm expecting the code to work is the most natural way for that author to have written it, and it's very obvious from the implementation. So, I don't care about these three questions anymore. And as for the pointer for getIndex, don't use pointers to express nullability. There's boost optional. You could pick a sentinel value if it's something like a uint or an int. You could have changed that uint to an int, and a negative value is the range of sentinel values, something like that. Because when I have the pointer, and I get the pointer which tells me the index, and then I have a bunch of operations, and I want to use that index again. If I didn't dereference that pointer up here before I made those three function calls, now I have to think like, did that change out from under me because of one of those function calls, or did it not? I'm thinking about lifetime, I'm thinking about identity, I'm thinking about addresses and memory when I should be thinking about what the program does, which is always in terms of value, not in terms of pointers and pointer chasing. Okay. Okay, so as another guideline, just keep raw and shared pointers out of your interfaces whenever you can help it. They make your code harder to reason about. When you have raw and shared pointers, they are a form of shared state. This is the moral equivalent of using global data in your program. Okay, so if I have a global global variable, if I've got 3 or 4 references to it, you've got the problem that references to it grow over time, and that becomes a problem. And it's just harder to reason about even among those 3 or 4 references, right? So I've got the consideration that one of those other 3 or 4 references might have changed the value out from under me at some point during my one of those scopes. Okay, so again, we don't want to think about lifetimes of objects. We want to think about what they do, because that's what the program does. Okay, so we covered these 4 things: that names are important, that there's this principle of least surprise we don't want to violate, that we should make our interfaces impossible or, if necessary, difficult to use, and avoid aliasing. But there's a common element of all these. And in fact, I would say that they're all saying the same thing, which is that your code must be easy to reason about. I don't actually consider these 4 different pieces of advice. I consider them different ways of saying a small part of the major piece of advice. Just one piece of advice: your code needs to be easy to reason about. These are 4 different ways in which you can make your code easier or harder to reason about, but it's the same piece of advice. All right, so composability I put in its own section because I think it's very important, but it's just an aspect of usability. Okay, so this is kind of more of the same issues. So I'm going to put some blanket assertions up here, and hopefully I will justify some or all of them, and hopefully some of them will just be obvious once you hear them stated in the way I'm going to. So first, I think type should be regular. Regular means that something is default constructible, it's copyable, it's assignable, it's movable, it's destructible, and it's equality comparable. If I don't have equality comparable, this is something called semi-regular, which you'll see in a second. It's also very useful. Copy and assignment, though, must not create aliases. So shared putter has all of this. It is not regular because when you copy a shared putter, you now have 2 references to the same data. They do not have independent state, even across copies. Okay. And like I said, semi-regular is often very useful too. If you have all the rest of these and you can't compare them for equality, that gets most of what makes regular useful. Okay. And here is what makes regular useful. Think of regulars like a number, right? Numbers are easier to reason about than C++ APIs. Okay, they just are. Right? You want to think about the world in terms of mathematical formulae when you can, and when you can't, deal with classes and so forth. Okay. Moreover, think about regulars like a banana. Okay, with the exception of copy, all these properties apply to bananas. Okay, so I heard someone say something very insightful during a talk one time. He said, people worry about the move from state of an object. This is a big topic in C++ 11 and later. If I move this remote over here, what happens to that remote? Well, there is no remote. This is the remote. Like, I'm not looking for the banana, or if this is the same banana as another banana. It's just a banana. There's not more than one reference to it. It's a banana. Okay. So if you can think about the world in this very simple way of like actual objects that live in your code. And I'm not talking about object orientation. I'm talking about the entities in your code are real things in the real world. If you can get the lifetime semantics out of your thinking, you will make more code that is more extensible, more maintainable, faster. Okay, and of course bananas are easier to reason about even than numbers. Okay, so functions should be pure. That means that they depend only on their inputs. They do not mutate their inputs, and they have no other side effects. Okay, mutating their inputs are obviously a kind of side effect. So remember XOR swap, right? We had a lot of trouble getting to a good implementation of it when we started from the point of view that we were going to make a function that mutates its arguments. So when you see this function call, what is an issue that comes up? You can shout it out, anybody. Order of evaluation, right. So we've got 2 function calls in the same expression. Which one happens first is an issue unless they're pure. Then I don't care. Again, we're not thinking about addresses anymore. We're thinking about what the program does when we write it like this. We don't have to think about like maybe foo does some crazy increment and then a test, and so I don't know if the 2 increments happen and which order they happen in, especially in case of inlining and stuff. So just get rid of all these things. Just make these functions pure. Okay. Type should define a basis. So a basis is a set of member functions, which is the minimal set of member functions that you need to maintain the invariance of your type. Okay. So that means you don't include anything else that is a function of the basis or that is outside of the basis, okay? As an example of this, why don't we have vector sort? Why isn't that a thing, right? It's dumb is why, right? we hopefully we don't do a lot of dumb things as a standard library convention. So we have stood sort, which is done in terms of vector or stood array, and it makes no difference which one you use, right? That's because we have standard algorithms that are done in terms of the 5 iterator categories. You have at most 5 implementations of any standard algorithm, and you can have an infinite number or simply unbounded number of container types, and they all have some iterator categories, so they all work with the standard algorithms. Okay, so we don't want to have a different sort for each container, and so that indicates to us that we shouldn't be adding things like sort that are extraneous to the basis of the type itself, okay? We define stood sort in terms of a subset of the basis, which is just begin and end on the containers we want to sort. So again, you should not add things that are extraneous to the basis. And when you employ that discipline, you're able to pull things out and generalize in a way that wouldn't occur to you before. So if instead of having stood sort, I had stood array sort and stood vector sort, I would implement each one in terms of the guts of that type, and then that code would not be reusable across those two. If I say I'm only going to do stood sort in terms of those other 2 APIs, in terms of the begin and end of those things, now I have to suddenly write code that is truly general purpose and can be used for both cases. And that doesn't apply to just containers and sorting. This applies to any 2 types that you've got that you want to do a common operation on, right? You will find ways of generalizing and writing generic code and being more productive if you enforce this discipline. Okay, so if you want to see a counterexample of this, you can look at stood string, which has a famously fat interface, which does the kitchen sink is in this thing, right? Recently, stood array view was proposed. I think it's in the Library Fundamentals TS, and the idea is you can pass in a const char star to this or a stood string, and then it has the interface of stood string, so you don't have to actually copy anything or have double overloads for efficiency and using a const char star in those cases when you've got one. The problem with it is that it has to reproduce the entire API of stood string, this giant fat API, right? If we had algorithms on stood string or a const char star that operated on strings of characters, we wouldn't need to reproduce all this API, and anyone that wanted a work-alike string wouldn't have to do it. Okay, this is an important point. All right, so also container types need to be interoperable with STL algorithms. So that means they need a begin and end. They need their own iterator types. So if you need to make a custom iterator to make this happen for your type, get to know the Boost iterator library, because it makes what is a thorny proposition, making an iterator type, a custom iterator type for your container, nearly trivial. So here's an example of the amount of code you need, and this is more or less cut and pasted out of their documentation. Here's the amount of code you need to make a forward traversal iterator, okay? So the top part where we're inheriting from a type, that type is just a CRTP-based iterator facade is what they call it. So you give it the type of the class we're making here. You give it the type of the underlying node that you've got, and then you tell it with this forward traversal tag that it's a forward iterator. And then the rest of it is kind of boilerplate. If you look near the bottom, you've got increment, equal, and dereference. Those 3 functions are where all the magic happens, right? That's where your actual implementation goes. So once you know that this is all the boilerplate you need, then you just do those implement those three functions that do what you actually care about, and all the boilerplate goes away. A lot of the boilerplate you have to do for a standard iterator is hard to get right. There's some subtleties that it takes some experience to do. This takes all that out of your hands. Okay, so you also need to make your types usable in range-based for loops. Okay, this is really important. Okay, so let me back up. So the reason I'm saying this is that I recently had a container that one of my coworkers wrote that did not do this, and we had to iterate across the elements based on index. I caught an error in his code that he'd already written, where he had a fence post issue with the iteration that was causing a bug, and then I wrote another loop that had a similar problem on the other end, the other fence post. Okay, so making range-based for loops usable by your code gets rid of those kinds of fence post issues. Again, it's obviating a whole class of errors that are possible without them. Okay, and this takes very little effort. So let's say I've got this custom array type and it's got some storage, say a std array or a vector or something. So all I have to do is make these two free functions that take a const ref to this array and then return the begin and end of its storage member, and that's it. Now I can use it down at the bottom. This is real code that compiles, and this custom array, I'm just iterating over it, and I get each element one at a time. I wrote the arrow decal type bit just so I didn't even have to know that the name of the pointed to value underneath there is, that the name of the iterator is iterator versus const iterator. I don't care. I just want to write whatever it produces. That's what goes there. And the nice thing is in C++14, everything past the arrows can go away. You just remove the arrow, whatever, and you just use automatic return type deduction. So this is getting easier and easier, and it's already easy right now. You should do this. All right, so library types also need to be used in a container or subobject. If I've got my type and I want to use your type in it, I better be able to have it as a member, and that better be easy to do. If I have to make your thing hanging off the end of a pointer inside my class, even if it's a unique putter, that makes it harder for me to get my work done. If I can't use your type in a std vector, we got problems, right? That's a fundamental data structure that we use every day, all the time. And so the most controversial part of the regular concept that I talked about before is that regular has default constructible. A lot of people grouse about this being a weakening of invariance for your type. So if you've got a type you can only construct certain ways and you don't want it to be nullable and you don't want it to have an empty state, then you don't want the default constructor. I argue that I care for myself more about being able to put one in a std vector and being able to call resize with only one element, which requires a default constructor. So that's just the way I work, and I really care about that. Some people really care about strengthening the invariance. That either one of these is fine, but think about this and consider that this is an important case for making your types reusable, even if it weakens the invariance. Okay, so regularity in general helps with composability a whole lot, right? If you're able to treat something as a banana, you throw the banana in the basket, you line up bananas on the table, whatever. They just go wherever you need them to go, okay? So library types need to be constructible anywhere that someone wants to construct one whenever possible. Everybody knows about constructing stuff on the heap and the stack. A lot of people don't really think about making something with a const per constructor. And they also don't really think about making something ROMable by making it, brace initializable in static scope, right? So if it's static init, but it calls new, then you're not going to be able to stick that in ROM. But if it's something that just has literal data types and sits in there, it can be const expr or just ROMable and non-const. Either one of those things is very nice. Okay. If you've got a type that downloads stuff from the internet and its constructor, then this doesn't work. But wherever it's possible to get those other two use cases, you should strive for that because, again, you don't know who's using this type and what their conditions for use are going to be. So error messages are important, but one thing that a lot of people miss when they're doing anything that involves any kind of template metaprogramming is that they're like, well, the compiler produces a spew of template errors, and what am I going to do, right? Well, if that is the case, your library is going to be unusable to a certain class of programmer. If you look at BoostGraph or BoostSpirit, they both are great libraries that do what they do very well. And if you make the slightest mistake, they punish you viciously for it with error messages. Okay, and so there's lots of people that I know that are hardcore Spirit developers that are like, I make one line change and I compile. I make a one line change and I compile. I make a one line change and I compile because that's the only way I can get any work done. If something like this is the library you're going to be writing, you need to come up with some kind of a convention that communicates errors to the user in a reasonable way. So I wrote a linear algebra library that had matrices with static sizes and a bunch of different types in there, inside the matrices. And I couldn't really find a way to stop, let's say you're doing a matrix multiply, like somewhere down in this, 3D nested for loop, you're going to have two types, and when you try to use them together, if that blows up, there's no way for me to sort of catch that from the outside that's going to happen. So I just have to live with this template error spew. But what I also did was I said that I'm going to use a substitution failure is not an error in, let's say, operator times, so that if these two matrices don't have the same dimensions, then I'm going to say like that function gets removed from the overload set. And so if you say a times b and the compiler says there is no a times b, then you know, oh, well, that means that they're the wrong dimensions of matrix, right? If you get this huge mess, then you know, oh, I made a mistake in the dimensions of the units I put inside, okay? Yeah.
What about static assert?
That's the next thing I was going to say. So I also made static asserts at certain places to catch certain conditions that I knew were common. And then when you go to that static assert, I had a big fat note saying like, this is why you hit the static assert, right? And I feel like that's a pretty good convention. And if you do any kind of meta programming, you need to come up with something like this to communicate problems back to the users. Okay, I've been saying should a lot. So what I want you to take away from all these shoulds is that you should strive for, it is impossible to use wrong, it is maximally efficient, it is maximally composable with other code, and then only compromise on that when you have to, and sometimes you simply have to, right? So I'm not saying you should get carried away and make something, like for instance, the example I gave before about making input iterators in your ranges. Like if you decide that actually you do care about indexing into that range, don't make this type with input iterators and say no one can index into it because I don't want that kind of error when it just gets rid of a whole bit of functionality you actually need in your library for some reason. Okay, so it's another case of don't get carried away. It's not wrong to use non-regular types and impure functions and stuff. Sometimes you need to for performance reasons. As I said before, if you've got a large object, you want to pass it by const ref. That's not, there's some cases in which that means the function is not pure, and that's probably okay. But again, get as close to that as you can. Have that ideal thing in your mind and keep trying to hit back to that, and then only compromise when you have to. Okay, so here's the grab bag of library implementation tips. So another claim I'm going to make is that implementation and design are synonymous for writing programs, right? You have some way you think you're going to implement code, and then you go to actually implement the code, and it turns out that you've got this complete impedance mismatch between unit A and unit B. They just don't cooperate without this other bit of functionality that you didn't realize you needed until you started implementing. This means that as you go, you need to be using your own code and refining where there are problems. Like this needs to be a constant thing, especially in the early stages of development. This is iterative. You're not going to get it right in the first pass. You're probably not going to get it right in the third pass either. Okay, and writing tests as you go really, really helps with this. Hopefully we're all testing our code, but realistically it doesn't happen sometimes and in some places. The more tests you write, the better your interfaces will get, not just the more correct they'll get. And start with just writing, fairly extensive snippets of what you want the client code to look like before anything compiles, before you've written a single line of your own library code, and keep referring back to that. And if you can't get the implementation to match the ease of use that you wrote when you said, if I had my druthers, this is what I would write, then again, go back and sand off those rough corners. So, and this is a process of discovering the right solution. You're not inventing anything new, right? Get very familiar with lots of other libraries. There are any number of library development problems, and they've all been solved by somebody somewhere. So read a lot of the code. And if you try something and it doesn't work, if you refer back to that example code you're writing as you go, and you find that something doesn't work the way you want it to, then you need to keep looking, right? The reason I say these things this way is that I find that a lot of people I work with are like, well, this works pretty well. And I'm like, we need to find a way to make it perfect. And only when we prove to ourselves that it's not perfect do we settle. And if you don't keep that mindset, it's easy to slip into something that's highly imperfect. So an important metric in this process, something hopefully everyone else has heard too, that you make simple things simple and not simple things straightforward to do. Okay, so the common case of use, you need to be able to write very succinctly and easily in your sample that you're working from, that is the target code you want clients to write. And if you find you're drifting away from that, you maybe need a redesign. Okay, so as an example, that should be Daxby. Okay, well, that says a lot about bad names. So Saxby is actually a float for the A and not a double, but these are actual functions from like a BLAS implementation. So like from the Fortran days, there's a standard BLAS API for doing linear algebra. And in this case, Saxby means single precision single precision A times X plus Y. That's what this thing returns, okay? Now, Daxby means double precision A times X plus Y. Okay, so there's a lot of them. They're insane names, right? So if instead I did operator star and operator plus, and I was able to write a times x plus y, everyone's going to know what I'm doing, right? This is obvious code. Everyone gets it. You don't have to know what Saxby and Daxby mean, okay? In order to get back to actually calling code that looks like Saxby or Daxby, you need to use something called expression templates. If you don't know what that is, don't write a linear algebra library, but it's a very heady topic, and there was a 3-hour talk on it yesterday to give you some idea of its scope. So in order to transform this into Saxby, and the reason you want to do that is because Saxby exists because that is way more efficient than doing the a times x by itself and then adding the y. Doing it all in one step is way more efficient. So again, you want people to write code like a times x plus y, but at the same time, you don't want to give up the efficiency. So there's an important point here, which is that, again, you want to refer back to like, what do I want my user code to look like? And if I have to jump through some insane hoops and do a bunch of gymnastics to make that efficient, then that's just what I have to bite off as a library writer, right? And compromising and saying, no, everything's going to be called Saxby and Daxby is not sufficient. Okay. So documentation is important to users. Some very large libraries have great documentation, and without it, they would be largely useless. I don't know if anybody in here has used Blue Spirit, but it's this huge parsing library that does all kinds of stuff, and it's got very extensive documentation. And without that documentation, you have no clue what this library does, right? There's lots of stuff in there. But aside from that, docs are very, very important to the implementation and design process. I have found myself so many times writing documentation that says the library does this and then realizing the library doesn't do that, right? I had thought that this is what I wanted the library to do, and when I actually implemented it, didn't do that. And then writing the documentation let me step outside myself and kind of realize that. It's the same phenomenon as, I don't know if a lot of people have heard of, explaining a bug to a teddy bear or whatever. It's like you don't need another person to help you debug it sometimes. You just need to step outside your normal frame of reference, and then you see things from a different angle. Writing documentation does the same effect. It's very, very handy. Okay. So you need to really anticipate future needs at the beginning of your library design process. When it's things like thread safety, that's very hard to bolt on later. Things like versioning are also very hard to bolt on later. There's a small set of things that are in this category of, if we didn't think of it at the beginning, we're kind of stuck. But there's another important aspect is, which is don't get nuts with the features, right? So I used to work at a place where we did visualization of sonar data, and there was this one little widget that had like a bunch of bars of data, and they went down the screen. It was like near range to far range, and then like direction around the circle went from right to left. So in this view, we're only rendering data in that way I described. This is near, that's far, it goes right to left. The guy that wrote it was like, well, there's no reason why it has to be right to left. There's no reason why it has to be near and far on the bottom and top. So he just wrote it all 4 ways. And there were like 6 levels of inheritance, and it was just a big mess. And it got to be such complicated code that is something relatively simple that he himself could not fix bugs in it that we found, and we couldn't extend it. We ended up throwing it away and redoing it, right? And so there is such a thing as too much generality. There is such a thing as too much genericity. If the direction you're going in is making it generic in a way that says, I want more and more features, you're probably on the wrong track. If it's generic in a way that says, like, this is the fundamental thing that it does, and I want to make sure that everyone that does it a slightly different variation of that can do it, then you're probably on the right track. Okay, so header only versus compiled. This comes up with some, especially open source projects. A lot of people say, like, if it's not header only, I'm never going to use it because it's too much trouble to figure out your weird build system and link to your library, and life's too short, okay? And then some people say, I'm never going to use your library if it's header only because I'm not going to like recompile that every time because I've got this very tight loop where I compile and I debug and I code, right? So you can have both worlds if you use this pattern that you'll see this a lot in the Boost libraries if you want another example of it. But essentially, you've got your header, it's got your interfaces in it, and at the end of your header, you say, like, if I've got this macro defined that says it's header only, then I'm going to include this IPP file. Okay, that basically has all your implementations in it. And then you've got your foo.cpp file, which unfortunately I should have written like include foo.h at the top of this. That makes this make more sense. But if it's not header only, if you don't have that macro defined, then you include the IPP file here, and then you add the CPP file to your build. Okay, and then the IPP file has the stuff you would normally have in the CPP file, except maybe the pound include of the foo.h. Now, you can do this with foo.cpp by itself. You don't need the IPP file necessarily, so you can include that at the bottom of your header file if you want. But something like this is very easy to accomplish if you just start with it from the beginning. It's no extra work. If you try to do it later, it can be difficult to unwind things. Understand how inline namespaces work. So inline namespaces, there's lots of great tutorials online, and I didn't really have the time to go over this in this talk, but suffice it to say that inline namespaces allow you to take, like, let's say you've got namespace foo, and you've got v1, v2, v3, all these different versions of your library. And so you just say, like, this one is the latest one. And then everyone just says using, or everyone just says foo : whatever, and they get the latest version of that API entry point. But then you can also have the older versions side by side with the newer versions in a very nice way. They don't conflict because they're in different namespaces, but as you migrate different versions, you always have one version that is considered to be the latest one that just uses foo : right? So, like I said, I'm not going to get into it too much. There's lots of great stuff online how to use it. It makes it very easy to version your library and migrate once you change versions, or for client code to migrate especially. Okay, so generic code. All templates have an implicit concept requirement, even if it's implicit. So let's take a look at this. Let's say you look in the documentation, you just see like the name of this function, and it doesn't have any comments. It's just this function and some lect oxygen comments or something. So it takes an A and a B by value. That elides the fact that A plus B is used inside of it. Okay, and so I can't pass just any old thing in there. I need two things that I can add. Okay, so there is a requirement on virtually any template you write that the template argument T or whatever argument has requirements on it for what types will fit in that template parameter. If you don't document them, then you're making your code like impossible to use in some cases. It'd be very hard to unwind these kinds of things sometimes. If you have the concepts feature, use it all over the place, right? In this case, this is probably going to be a concept that comes with a standard library, arithmetic. And if you just put arithmetic T on your sum function, then all is well. People are going to know what that is in a few years when this is a common feature. Until then, document these things, right? If you have a public function in your library API that people were expected to use, they need to know what the requirements are for T and U and all the other template parameters you've got. All right, so to boil this down, we're writing libraries for code reuse. That's it. That's the beginning and the end of why we do this. Okay, and because of that, we need them to be maximally efficient, and we need them to be maximally reusable. In practice, what this means, these are the guidelines that went over in the second half of the talk, that means you need to make your library API easy to reason about to get the usability part. And that means that you need to name things in a way that is obvious what the names do. You need to make sure that the functions don't do anything extremely surprising in addition to doing what the names say they do. They don't have any crazy side effects. You need to make the interfaces impossible to use incorrectly wherever that's possible. It's not always possible, but at least make them hard to use incorrectly. Avoid aliasing. Type should be regular, function should be pure, and type should define a basis and nothing else. All other things should be free functions. All right. Also, container type should be interoperable with STL algorithms and usable in range-based for loops. And types should be usable in a container or sub-object that someone else writes. Your type should be constructible anywhere. Don't forget about making things ROMable where possible or const export where possible. And error messages can't impede the use of your library, or you've got a library nobody can use. And finally, don't stick to every one of these guidelines all the time, right? Right. Like, so the thing I keep saying is that you want to strive for every one of these bullet points. Every time you're making a decision, you're like, am I compromising on any one of these? And if the answer is yes, why am I doing that? And if that's not a compelling reason, don't do it, okay? That doesn't mean there aren't compelling reasons. Do it in those cases. All right. Ooh. Questions? Yeah.
So do you have any suggestion on how to design the folder structure for an optionally header-only library? Because when I actually implemented some libraries that were optionally header-only, it was pretty annoying to have the global include and source folders, as you had to use absolute include paths to include the CPP file in the header file, whether or not you had the header only macro. And something I used was actually having like a folder for every module of the library and have a local include and source folder inside the module folder, if that makes sense. So do you have any recommendation on how to design a nice folder structure?
I really don't. I mean, a lot of people really swear by having an include and source breakdown where the include has like the whole tree. A lot of people swear by, like you said, a module breakdown where you've got include and source. To me, it's 6 of one, half a dozen of another. As long as it builds, I really don't care about the layout that much. Whatever the layout is, I'll get used to it. And I think most people are like that too. So yeah, I don't have any concrete recommendation for that. So yeah, go ahead.
So we're involved with writing libraries and stuff. One of the things we've had a hard time is picking, okay, when can we start using new standards as they come out for compiler or whatever? Do you have any recommendations on?
So the question was, how do you migrate to new standards of C++? Essentially, when you've got
When
right?
How long do you wait before?
Oh well,
new standards?
How long do you wait? That's a big question. I mean, essentially, where most places work, like you've got GCC, Clang, and Visual Studio. If you do really lots of cross-platform stuff, and you need to make sure they're all three using whatever feature you want to pick, and of course, downstream clients have to be able to do that too. So I don't think there's ever a particular good or bad time to migrate. As long as your downstream clients are able to compile and use that code, then that's the time to do it. As for using specific language features, I think that the nice thing about C++11 is the vast majority of the language features that are new are also things that are, they're just pure extensions. So if you want to start using them in some places and not in others, that's totally fine. And then you can just, migrate stuff as you go. So that is a nice aspect of that standard. So good.
So you mentioned that we should document the concepts, essentially, even if they're implicit.
Right.
But following the advice about compiler errors, shouldn't we actually implement sort of concepts like with enable if and then static asserts in a catch-all to give them good compiler errors? Right.
So the question was, instead of documenting requirements for template parameters, the constraints on them, instead use enable if. So there's sort of two schools of thought on this. Like one is use enable if, and that's great because it pulls things out of the overload set, and that's one way that a user can detect that they've chosen the wrong instantiation for this template. The downside of that is it's completely removed and something else might get picked up. If you've got a static assert, that's the other way of doing it, which is that we're going to let you try to use that, but we're going to tell you why it's wrong with a static assert. It completely depends on, like I said, I had this convention before where I had certain things I would catch with a static assert, certain things I would catch with Svine, certain things I wouldn't. And it just depends on how you're breaking things down. The important part is you come up with a good convention that is consistent and it generates this kind of error for this kind of thing and that kind of error for that kind of thing. And when a user sees an error, they know immediately where to start looking for what kind of error it is. So that is a great thing to do. But it's not necessarily the only right answer. So,
do you have a compelling reason why I should construct my library to be header only? Header only?
No, I don't. But there are. I've seen people over and over and over say online when talking about a particular boost library or another library that they're going to use or not going to use, I'm never going to use that because it's header only. I will only use that if it's header only. It's just user taste. So if you have lots of users that care about this, make it possible for those users that care about header only to get header only, and those users care about compile only to get compile only. That's my advice. I don't have a particularly compelling reason for either one. I personally don't care, but lots of people feel very strongly about one or the other. So yeah.
Level. Oh, sorry. At the API level, do you have any recommendations for taking a library that maybe is not in a good state currently and getting it into a good state if you have a lot of callers?
A lot of callers?
A lot of people are consuming it already.
No, you're kind of stuck. That's sort of a big problem. So another one of the things when I said before, think about thread safety, think about versioning. The big part about versioning is thinking about okay, we've got this API entry point. Once we publish this and downstream users are using it, we are very much locked into that. We can give them an alternate API, but a lot of people can say we're not going to rewrite all our code for this incremental gain that's rather small. So my advice for you is make make APIs that wherever possible are completely extensible. So if that means you do something that's pessimal, like you pass in a struct that you can add members to, or you pass in a handle to something that has the configuration, if there's some fundamental entry point in your API that cannot change once you publish it, and then any further features that need to happen need to be able to fit within that, you might have to do something like that. And like I said, passing in a handle to a configuration object or passing in a struct, these are pessimizations. Like, these are well-known things not to do to make optimal code, but for purposes of making things general purpose and making them extensible, sometimes you might have to do that.
Just to the question of why header only, at least in our case, our build environment is set up, the way we use link time optimization and whole program optimization relies on us being completely header only. Now, there's other ways of setting up the builds and so forth to get different optimizations, but that's our reason.
Okay, wasn't aware of that. Anybody else? Yeah.
What are some good libraries to look at?
What are some good libraries to look at? One of my favorite libraries in terms of linear algebra is Eigen, because it does lots of very nice stuff. So it essentially takes stuff like I was showing you before, like, you know, the x times a times x plus y. It takes something like that and transforms it into something like Saxby, and then it also takes the extra step of saying, if I know that I can generate vector code for this, I'm gonna do that instead. So it takes stuff from a very simple to use interface that looks very easy and does a bunch of insane gymnastics and produces the right stuff, right? Other libraries, like if you look at, like, most of the Boost libraries are very, very high quality. Some of them do really interesting things with metaprogramming that are just fun to look at. Like, I don't know that you're necessarily going to try to do the same thing in your own code, especially if you're using C++ or 11 or 14. You don't have to do a lot of those things anymore, especially 14. You basically don't have to do metaprogramming in 90% of the cases where you used to. Yeah, looking at the Boost libraries, I mean, the first time I read Boost Any, I was like, why doesn't everybody do this? Why didn't I think of this myself? It seems like impossible that any should exist, and then the implementation is very simple. That's a great sort of aha moment. So, anyone else? All right, I think it's it. Thank you.